Hey guys, so let's solve a problem in which you have a string, okay, that wraps around a pulley, right? And then the pulley is falling under the influence of gravity, okay? It's just like a yo-yo, right? So you have a mass that's hanging and it's falling down, right? And it's rotating, okay? Not a very good one, but it's just rotating, okay? So so the forces acting on the mass, right, are tension, right? So this is tension, and this is weight, right? So you're holding the mass, and the mass unwraps and falls down, right? Just like a yo-yo, right? Now, how do we solve this system? Let's see. So we can now this is rolling motion. Okay, this is not rotation. This is rolling motion. Okay. We solved a problem in which a mass was hanging from a pulley, right? Um, and the pulley was rotating. So that was rotational motion, and we connected a linear motion to rotational motion. This is sort of the other way around, where the pulley falls down. Okay. Now this is rolling motion. Rolling is a rotation plus translation. Okay. So we can use multiple approaches to solve this problem. Okay. So we can write Newton's second law so there is linear motion. So there is translational motion, because rolling is a combination of translation plus rotation. So we can therefore write Newton's second law for the linear motion of the pulley as it falls down. So we can write W, so that's F net equals mass times acceleration. So this is the direction of the acceleration of the pulley or yo-yo, whatever you want to call it. So W minus T equals ma. Now, tension, you can see, is the reason why this pulley is rolling. Okay, it provides the torque that the pulley experiences, right? So we can also write, for this part of rolling motion rotation, we can write Newton's second law of rotation. Tau net equals I alpha. And we'll assume that the pulley is a solid disk, and for that we have I equals half m r squared. Okay, so there's just one mass involved, which is the mass of the pulley. This is also the mass of the pulley. We're assuming that the string is massless. Now that gives us this was F net equals ma, tau net equals I alpha gives us T times R equals I alpha. Okay, and tension is therefore I alpha divided by R. Okay. Now alpha is A equals alpha times R. Okay. So alpha is A divided by R. So we can plug that in. So alpha is A divided by, so we get tension equals IA divided by R squared. Now you can see that I over R squared is just half of M, right? So you get tension I over R squared. I'm going to put half of M times A. Okay. So we actually get an expression for tension, which is just half of mass times acceleration for the pulley. So let's call this equation 1, this equation 2. So let's plug 2 and 1. We get W minus half ma equals mass times acceleration. So we're getting a very simple expression. Actually, you can see that W equals 3 by 2 mass times acceleration. Now W is just mg, so you get mg equals 3 by 2 mass times acceleration. So acceleration of this yo-yo is 2 by 3 times g. This is the acceleration. It's interesting, right? So you get a very simple expression for the acceleration of the yo-yo. Now you know the acceleration. you can actually, now let's say that the yo-yo is released from rest, so you can use this equation v equals v naught plus at. Then if the yo-yo is released from rest, then you just get v equals at, right? Where a is just 2 by 3g. Or you can also use this equation, v squared equals v naught squared plus 2a delta y. So if v naught is 0, then you get v squared equals 2 times a, which is 2 by 3. So it's 2a delta y. So that 2 by 3g gives you 4 by 3g. Let's call delta y h. So keep this in mind. Let's see. Let's apply conservation of energy, and we'll see that we get this expression from conservation of energy also, right? In second law are just they're connected with conservation of energy, so we'll just demonstrate that quickly. So let's say that the yo-yo starts from rest, so it falls a height h, so it has potential energy that's converted into the kinetic energy due to rotation plus kinetic energy due to translation, because rolling is a combination of rotation and translation. So you get mgh equals half mv squared plus half I omega squared. This is the rotational kinetic energy, right? So and this is the velocity of the center of mass. The center of mass is this. So this is the velocity of the center of mass. Remember, in rolling motion, every point on the object moves with a different velocity. Okay. So this is the velocity of the center of mass. So now we can simplify this further. We know that we're dealing with a disk over here. So mgh equals half mv center of mass squared plus half m r squared, and then omega squared is v squared over r squared, because v equals r omega. So I'm just going to plug in omega equals v squared over r squared. So the r squared cancels out. You get mgh equals half mv center of mass squared plus 1 by 4 mv squared. This is also v center of mass. Okay. So you can see that so the mass cancels out, and you get gh equals, so that 1 by 2 plus 1 by 4 is 3 by 4. Okay, v center of mass squared. So v center of mass squared is 4 by 3 gh. Interesting, right? So this is the velocity after it falls a height h. You can see we got the same answer. Yeah. Okay. So in some cases the question might ask you for the tension, then you have to definitely use this approach. And if it just asks you the velocity, you can use any of these. But of course, conservation of energy is always an easier way, a much powerful way to solve a problem. So this was it for the yo-yo, right? Well, a very primitive yo-yo, but it's just how you can analyze the yo-yo. Let me know if you have any questions. Post them in the comments, and if you like the video, please press like and subscribe. Thank you.